All right, so this is part 2 of our discussion of sentence embedding for semantic similarity. So we've looked at 4 methods. You should be seeing the code right now. We looked at 4 methods for comparing similar and dissimilar sentences. So we looked at using glove and average pooling. We looked at GRU, which uses glove and RNN. And then we use a non-specialized BERT model. So just pre-trained, no fine tuning, which did worse actually than the other methods. And then we looked at the specialized SBERT embedding using this pre-trained model here. And this actually did really well. So if we look at the results here, you should be seeing now the output on the terminal. And you can see that the results, glove was, not very noticeable difference. BERT non-specialized was actually bad, but here when we use SBERT, now it does really well. So that's good, right? We have a technique now or a tool for sentence similarity, which is something that could come in handy. All right, so given this, and it's a pre-trained model for that task. Now, what we're gonna do is we will do a harder similarity test by choosing text that's a little bit more tricky. So we're gonna go over here. So this was our SBERT model. Now I'm gonna just copy this text here. Copy. And so we're gonna go over this one. Okay. So now we will do a harder similarity test with tricky sentences. So whereas before the sentences were, a black dog walking beside a pool, a black dog is walking along the side of a pool, versus dissimilar, a little girl and boy are reading books, then an older child is playing with a doll while gazing out the window. So those were dissimilar. Now we have tricky sentences, and we're going to perform the same task with the 4 methods and just see how it performs. So look here, for instance, we have a couple of samples of tricky sentences, contradicting sentences. So for instance, an elephant is bigger than a lion. A lion is bigger than an elephant. You can see how they are tricky, right? They're not really similar. Or the cat sat on the mat sat on the cat. Do you guys get the basic idea there? So we're gonna use, we're gonna measure the similarities just to see which one does better. So let's go ahead and run this. You should be seeing the prompt. Okay. Okay. Okay, that's perfect. And there we go. So it thinks that, so average glove just thinks they're similar, right? And BERT thinks they're similar, and even SBERT thinks they're similar. Actually, only GRU thinks they're dissimilar. Why do you think that is?
Is it the sequence that is getting brought up?
Yeah.
It's the sequence, right? Because RNNs consider sequence, so they, whereas glove, it literally just averages, things. GRU actually is considering sequence. So if we go back to the code, an elephant is bigger than a lion. Here, the order, a lion is bigger than an elephant, so bigger, what is bigger? A lion is bigger than an elephant. Whereas here, what is bigger? An elephant is bigger than a lion. So the order mattered to the RNN GRU technique. And so you can see how sequence can be useful here, and it was, in fact, right? So for contradictory things like this, maybe your best bet would be something like GRU. However, transformers have also tried to address this issue. Okay, so we can go ahead and try, and this is the last piece of code today. We can try this model. Go ahead here. Oops. Just plug this here. Okay, so here we're gonna try, because we're gonna try a transformer, but we're gonna need a specialized BERT again, right? So we're gonna need a fine-tuned BERT. So we need a BERT specialized for this problem of contradicting sentences. Now there is a model from XNLI for this task. Okay, there is a model to detect the semantics of two sentences. Basically, this model has, for pairs, it predicts classes. It's going to say neutral, contradiction, or entailment. And so we will use a fine-tuned XLM Roberta model trained on XNLI. So this is the task XNLI, where they have actually annotated examples as contradictory, neutral, entailment. And XLM Roberta is just, well, it's a BERT model. Hopefully you've now spotted the in joke, right? That all the names include the word BERT in it. And this is XLM. These are very large models, like on the order of 160 terabytes or more, I think. So it's pretty large. 160 gigabytes, I think. Okay. So, this is the model, right? And so this is the code. So it's a little bit different, because here we are actually, doing a specific classification type of model. So let's go ahead and discuss the code. So from transformers, right, we're going to import the auto model for sequence classification. So remember, this is the classic Hugging Face for sequence classification object. We also need the auto tokenizer. So we call in the model and the tokenizer. The model is Joe Davlin, I think. This is Davlin. XLM Roberta large XNLI. Notice it's a large model trained on XNLI. And then the tokenizer. So you've got both of these. And now we're going to do the comparison. So tricky pairs was the text, right? We have it here. So from premise, hypothesis, and tricky pairs, right? We get the two sentences. We're going to use tokenizer.encode, which allows us to actually encode both at the same time. So we have premise and hypothesis. It'll return a PyTorch tensor. Notice that if we wanted a TensorFlow, we would say TF, but when we want PyTorch, we use PT. And the truncation strategy is to truncate the premise, okay? So that if it doesn't fit in the 512 tokens. So that creates the encoding X, and then that's an object, and then we just encode with the NLI model we predict, right? So we tokenized it here. And after tokenizing, we predict with NLI model. And then this just returns the logits that we're going to use. So remember, this is a classification problem. So it'll return 3 logits, right? So we can print them out. print logits here. We also print the premise, right, before tokenization, and the hypothesis, just so that we can see them. And then we do an NumPy argmax from the vector of 3, just so that we can select the IDs, right? And then from those IDs, we're gonna run them through the dictionary ID to label, so that will give us the label that we want. So this gives us the ID 012, plug in 012 in here with, you know, one of the 3, and then it'll give us the label, which would be neutral, contradictory, or entailment from the NLI model configuration parameters. And then once we have that, we can also view the softmax scores, right, by just iterating through the logits, basically. So we're going to do print NLI model config ID to label. So we print out basically the 3 labels. And for each one, we're going to print out the logit that was assigned to it. Okay. But we also know what the ID is. And then we just print out like a line here. So let's go ahead and run this one. So I'm going to do, and you guys should be seeing the prompt. Run it. There it goes. That's the model. So it's just, you know, oh, error. Oh no. Again. You should be seeing the prompt again. Okay. Okay. All right. And it finished, right? So we can see here. This is basically where the output begins. So we printed out. Oh, let's actually read some of this. It might be interesting. So some weights of the model checkpoint of Joe Davlin's were not used when initializing XML Roberta for sequence classification. This is expected if you are initializing XML Roberta for sequence classification from the checkpoint of a model trained on another task or with another architecture, e.g. initialize on model from BERT for pre-trained model. Then it says, future warning, the truncation strategy argument is deprecated. Use truncation equal true to truncate examples to a max length. You can give a specific length with max length, like 45, or leave max length to none to truncate, e.g. 520 for BERT. So remember this, Kyle, we were talking about that. BERT has a maximum of 512. Yep. If you have pairs of inputs, you can give a specific truncation strategy selected among truncation only first. We will only truncate the first sentence. And then the other one, I think there's some text missing. We'll truncate the second or longest first, etc. All right, so this gives us the 3 values of the logits. So basically this was the class, right? That was selective, 0. So the premise is an elephant is bigger than a lion. The hypothesis, a lion is bigger than an elephant. We want to know what they are, neutral, contradictory, or entailment. The class is contradiction. So that's correct. The softmax scores for contradiction were here. You can see. This is the softmax version of this, right? Which makes it 99 and the other one's close to 0. For the second sentence, we have the vector here. The premise is the cat sat on the mat. The hypothesis is the mat sat on the cat. According to this is entailment. The softmax is 49.07 and 49.9. So it was kind of close between contradiction and entailment, like extremely close. Do you guys see that?
Yes.
Does this make sense? Are there any questions or thoughts? Would you agree with these results?
I mean, I agree with the first one, and I can understand why the second one is as it is.
Yeah, an elephant is bigger than a lion is bigger than an elephant. The cat sat on the mat sat on the cat. Yeah, so it's not perfect, I mean, but at least this underscores a couple of techniques that we have for semantic similarity. So we have seen average pooling based, GRU based, and then we saw some transformer based, both just pre-training and fine-tune with a classification problem and a specialized data set. So I encourage you guys to play with this, you know, add other sentences that you can think of and just kind of, you know, see what you get. All right, so that's the code for this task. And then all we have left for today is we're going to cover, as I said, Roberta, as it feeds in from BERT itself. So before I move on to that topic, are there any questions on this? No questions or comments? Well, you have now a new set of tools in your toolbox. Okay. So that's good. All right, so this was somewhat easy, right? There are no questions, I guess. Right, guys?
Yeah, this was pretty straightforward.
Okay, great. All right, so now that we've finished this topic, so let me close this. I don't need this anymore. All right. All right, what we're gonna do now is we are going to talk about these papers. So let me bring them up. All right, so yeah, I'm gonna just do this with you guys. So let's let me share the screen. All right, so one of the main reasons for doing today's exercise was to kind of show that BERT is, you can kind of link it to Word2Vec, to the embedding techniques, right? It's a type of embedding technique. So that's what we saw today, that we can take inputs, convert them into embeddings, and then do similarities. we saw that if we just use the pre-trained embeddings, they're not great. But if we use fine-tuned ones, they might be a little bit better. So now let's bring up BERT paper. It should be this one. Huh. Okay, so this is the BERT paper that you should be from, you know, it's really important. Then I'm going to bring up also the Roberta paper. So are you guys seeing me looking for these?
Oh, yeah, we
Yes.
did.
This is the Roberta paper. Roberta, a robustly optimized BERT pre-training approach. Okay. And then the last one is unsupervised cross-lingual representation learning at scale. Right, and this is Roberta XLM basically. Yeah. All right, so we're going to talk about these three papers kind of in sequence. So I'm going to start with BERT. So now that we've been exploring this quite a bit. So I started talking about BERT last week, of course, and I'll just kind of emphasize some of the things I said. Notice this is by Davlin et al. It's Google AI. All right, this is a very nice paper. I highly recommend that you read through it as it talks about the history. Notice that BERT came out in 2019. All right, so the BERT's pre-training deep bidirectional transformers for language understanding. The whole idea of bidirectional just means that if you predict text, right, you usually predict it in a sequence. So that cat is, so what's the following word? Sleeping. That cat is sleeping on the bed. So in those models, you would only look at the words to the left, right? But they wanted a model that would look to the words to the left and the right. And that's where that's called bidirectional. And the way that works is, if we go to the whiteboard, it's basically the idea that you have, in a masked model, you have the cat is masked on the pillow, right? And so it's kind of bidirectional because you're going to predict this word, right, through the transformer, but you're looking at all of these words and you're looking at all these words, right? So that's kind of how they solve that problem with the masking. An idea by Taylor, 1953, right? You can, it's got a specific name for that. It's kind of a nice name. You guys can look it up. Oh, close task. So this is called a close with a Z, close task. All right, so anyway, this is the, where that bidirectional comes from. So, they go over the story here of BERT kind of nicely. And they basically, what they do is they pre-train it on a large data set, I think of 16 gigabytes of data. So think about that. And then the pre-trained model, then they fine tune it on several tasks. These tasks are called like glue, squad, and multi-NLI, and so on, right? And then they compare it to what others have gotten, and BERT just defeated all of them. If you look, the history starts kind of with word embeddings themselves. So they start talking about that. GPT was actually first, I believe, because GPT tried to implement the original Vaswani paper. There's also something called Elmo, and Elmo tried to do from left to right and from right to left through it with an RNN and then combining it. So it's kind of like convoluted, but it's important, I think, in the history. Okay, so you can see here, talks about BERT. Basically, it mentions that BERT is trained on the two tasks that I mentioned last week, which are the masked objective and also the next sentence prediction task. Okay, so it does both of them in the pre-training phase. So just refer back to last week's video if you don't remember what that is. Okay, so this talks about the history. Here is Mikolov, right, which is word to vec. So it kind of starts with embeddings like that. Mikolov again. And then it starts to get into others that have contributed in the story. So I definitely recommend you read through it. Elmo, which tried, as I said, left and right. And then finally arriving at BERT itself. Then it talks about fine-tuning tasks. All right. Oops, sorry, I didn't do that. So we were here. Then it talks about the fine-tuning tasks. These are, the glue benchmark, right, and so on, which are data sets that you train on. So here is the example for BERT of pre-training and fine-tuning, right? So remember, with pre-training, the masked sentence, right, prediction task, or so-called MLM. All right, so it's going to try to predict these, and also the next sentence. Notice this is the diagram. It's got the next sentence prediction, right? So I drew this last week as well. So you start with a CLS task, and this is the encoding, which now you can say if these two sentences are current and next sentence or not. As far as the fine tuning, once you have a BERT model, then you can fine tune it on any one of these specific tasks that you have here. All right, so this talks a little bit about BERT and some of the specifics of it. Okay. All right. So the BERT model architecture, it's talking about it here. Notice that BERT base, these are the specific values, and then these are the specific values for BERT large. Notice that the number of parameters for BERT base is 110 million versus the number of parameters for BERT large, which is 340 million. So what are those? Remember, those are the weights, the biases, etc. And you can see how it's much, much bigger. Other things are like the size of the hidden layers is 768 here, whereas here is 1024. The attention heads, here you have 12, here you have 16, and so on. Base is comparable to the original GPT as they were comparing against each other. So we've already talked about inputs and outputs last week. Okay. We talked about in the pre-training phase, remember that BERT has two objectives, the masked language model, task 1, right? So we talked about this, and then the next sentence prediction, or task 2. BERT, the people at Google believe that the next sentence prediction is really important for things like question and answering. What they did in this example, in this work, is that they would run the transformer without training it on masks or without training it on next sentence prediction. And it is their belief that next sentence prediction is really important, although others are saying that it isn't. So it's kind of a open question currently. To me, it sounds very intuitive, but you know. Okay, notice here, it talks a little bit about how you give it one input, the CLS, and then you get the output token. Notice that the final hidden state corresponding to this token is used as the aggregate sequence representation for classification task. So this is what I said to you guys before. That first token, the output of it is the encoding of the whole thing. Notice that they use word piece for the embeddings, for the subword embeddings, and the vocabulary was 30,000. Okay, you can see here, you have the inputs, the CLS tag, my dog is cute, separator tag, he likes to playing, separator. And then this is, you do the embeddings from a word to vec perspective. You also do a segment embedding, which you see here. It marks the first sentence as A, and then the second sentence is B. And then it's got positional embeddings, which basically tells you the sequence, right? So my is 1, dog is 2, is 3, and there's several functions that are used to capture this information. But it does capture sequence, just like RNNs capture sequence, this captures sequence, just the way it does it is different. For the pre-training corpus, they use the book corpus, which has 800 million words, and the English Wikipedia, which has 2,500 million words. Okay. Now that's the pre-training phase. Then comes the fine-tuning of BERT, and this was fine-tuned on the specific tasks that are available. So you can see those listed out here. You've got GLUE, which stands for the General Language Understanding Evaluation Benchmark, which is a collection of diverse natural language understanding tasks. Okay. And so they basically just fine tune it on those data sets, and then they, you know, have a holdout data set and they test it basically. All right, and then you can see them here. These are the GLUE test results. So you can see that these are other algorithms, for instance, GPT, right? So GPT is another one. And then this is an LSTM RNN-based model. And you can see that they've highlighted that all their results are better, right? So like, oops. Oh. So you can see here, the average was 82 versus 70s for all the other tasks. So for instance, this is, I think this is sentiment analysis, SST, and then QN is probably question and answering. Is this making sense, guys, how this works? That you grab several data sets and then you have trained data for specific tasks like question answering, sentiment analysis, and then you train the models and you compare it to other ones and you measure performance. Is this clear?
Yes.
Right. And then notice it just uses standard metrics like F1 score. Notice that usually a BERT large is better than a BERT base. So this kind of says the more architecture and the more data, the better it'll do. You can see all of these values are better. So that's the GLUE task. SQUAD, that's the Stanford question answering data set, which is a collection of 100,000 crowdsourced question and answer pairs. So given a question and a passage from Wikipedia containing the answer, the task is to predict the answer text span in the passage. This is a little bit more complex of an algorithm, but BERT trained on it. For SQUAD, you can see here the question answering, and it did better than all the top performers. Okay, or at least consistently, although it seems like it's got the highest scores. There's actually a SQUAD 1.1 and a 2.0, where in one, you actually have to, or when in the harder one, you actually have to tell in one, I think the answers are in the text, but in one, the text may not have the answer. So it's a more difficult problem. So it talks about squad too. So I definitely recommend that you guys read through this. Okay. SWAG, that's the situations with adversarial generations data set, which contains 113,000 sentence pair completion examples that evaluated grounded common sense inference. Given a sentence, the task is to choose the most plausible continuation among 4 choices. And you can see it, they believe it did better. They compare it a lot to GPT, which came first. Ablation studies just mean now we're going to play with the parameters and see which one is better. So the effect of pre-training tasks, like what if we don't use next sentence prediction or mask prediction, et cetera? How does the algorithm perform? Also the effect of the model size. So that means, what if we add more layers, more neurons, more data? And basically the conclusion is that I think, at least for this, is that the more data is good, but only if you can increment the size of the architecture. Okay. So these models are getting even bigger and bigger every day. Yeah, so that's kind of the parameters. You can see here, the parameters, the models. This is the conclusion, of course. You can read through that. And as I said, I had explained this a little bit more. So that's, Now, one thing that's interesting here is this. For the masked model, notice here the masked language model and the masking procedure. Let's take a look at an example of how it actually does it. Assuming the unlabeled sentence is "my dog is hairy," they're going to randomly pick about 15% of the tokens to be masked. And actually, they get chosen. 15% of them get chosen for a procedure, but they don't all get masked. So actually, what happens is during the random masking procedure, they choose, let's say here they choose the 4th token, hairy, right? So hairy. So the procedure then, the masking procedure then will do the following. In 80% of the cases, or 80% of the time, they will replace the word with the token mask. But 10% of the time, they will replace it with a random word like apple. So my dog is hairy, my dog is apple. And then 10% of the time, they will just keep the word as is. And so they don't, they take the sentences, 15% of them get chosen for this procedure, but not all of them get the word mask, and then you have to predict the word. Instead, some of them actually don't get the term mask. They get another word or the word, or keep the word. And according to them, the purpose of this is to bias the representation towards the actual observed word. So it's just a way of, if you think about it, the majority of the cases, it's going to be a mask token, but then sometimes it's a randomly selected token, or they just leave the word. So the way that I interpret this is that they give more emphasis to this procedure. So according to them here, that says, the advantage of this procedure is that the transformer encoder does not know which words it will be asked to predict, or which have been replaced by random words. So it is forced to keep a distributional contextual representation of every input token. And so that's kind of the idea there. It's like a biasing towards predicting the correct word, basically.
Here is the comparison of BERT versus GPT versus Elmo. You can see that in GPT, you only consider sequence. So given E1, you go to E2 and then to EN, right? So you're always predicting to the right. Elmo tried, if you notice, to the right and to the left. It had two models, right? So this one's going to the left, this one's going to the right, and then it did an average. BERT does everything with everything by doing the mass model. So everything is, you can attend to every single one. Here's a representation of the next sentence prediction. So basically you have the man went to Mask's store, he bought a gallon of milk, right? So these are two sentences separated with a separator, and the label is that is next. But in the next example, you have the man Mask to the store, and then the second sentence, penguins are flightless birds. So that's not next. So this is the other procedure that you use to train BERT. Then these are just some of the parameters of the model. According to this, training of BERT base was performed on 4 cloud TPUs in pod configuration, 16 TPU chips total. Training BERT large was performed on 16 instead of 4 cloud TPUs, a total of 64 instead of 16 chips. Each pre-training took 4 days to complete. Parameters for fine tuning, batches of 16 and 32. So that's good. The learning rates, here are the values. And for fine tuning, the epochs are not that many. Okay. Here they have a comparison of BERT, Elmo, and GPT. So you guys can read through this. Talks about GPT, how it was trained. So GPT trained on the book corpus, 800 million words, whereas BERT trained on the book's corpus, 800 million words, and Wikipedia. Okay, a little bit about the encoding. GPT was trained on 1 million steps with a batch size of 32,000 words. BERT was trained on 1 million steps with a batch size of 128,000 words. These are the individual fine-tuning tasks. So we've got for glue, multi-genre natural language inference, question pairs, questions and answers. Here's a nice diagram of how the fine-tuning works. So this one is for sentence pairs. So if you notice here, you give it as input CLS, the sequence of tokens for the first sentence, the separator token, the sequence of tokens for the second sentence. Feed it through the BERT, and then the class label comes out here. And this is called a sentence pair classification task for things like question and answering, or whatever these are, but it's comparison between two sentences. They have another one, which is the single sentence, similar. Class label comes out here, CLS, but notice it's only one sentence. So this is like, guys, can you hear me?
Yes.
Yes, we did.
So this is for like sentiment analysis, for instance. Then we've got question and answering tasks, like the task where you have a paragraph, and then you want to find out what segment of that paragraph is the answer to a question. So here we have input is CLS tag question, first sequence, separator token, the paragraph is the last sequence. And then here, the output is going to say where in, because notice that this is the paragraph, right? So in the paragraph comes out here, but it's going to tell you where the answer starts and where it ends. You see that? So it's just going to mark all the things in the span, basically. And that's how it knows it, based on training, of course. And then you've got the last one, which is the token classification. So like part-of-speech tag and named entity recognition. So you have CLS, single sentence sequence of tokens, goes through BERT. And then for every token, it's going to say, oh, not an entity. Person is an entity. Oh, not an entity. You see that? So these are for the fine tuning, the various architectures that BERT follows. SST is the Stanford Sentiment Tree Bank. So it's sentiment analysis. COLA is the corpus of linguistic accessibility, which is a binary single sentence classification task where the goal is to predict whether an English sentence is linguistically acceptable or not. So this is a little bit similar to what Joshua Thomas is thinking about. The STSB is the semantic textual similarity benchmark. So we did something similar to this today. MRPC is the Microsoft Research Paraphrase Corpus. So that's another one of the tasks. Entailment, NLI, we did some of that today. And then they looked at different questions for BERT. Does BERT really need such a large amount of pre-training to achieve high fine-tuning? Yes, BERT base achieves almost 1% additional accuracy on MNLI when trained on 1 million steps compared to 500,000 steps. So you do need large amount of pre-training. Does the MLM pre-training converge slower than other methods? Yes. Here it's comparing BERT base with masked and with left to right. So masked approach seems to be better. So they're just basically here, changing parameters and trying to figure out how it does. And that's it, right? So that's BERT. Any questions? Guys, any questions here?
No questions.
All right, great. So the next paper we're going to look at is Roberta. So remember, BERT is the original Google version after GPT came out. Now we are going to look at Roberta. So let's switch to that paper. So this is Roberta. Notice the year, July 2019. So this was now Facebook. They saw what Google did, and they wanted to try their own. They did this in collaboration with the Paul Allen School of Computer Science and Engineering at the University of Washington. So this is Liu et al. Okay. So what is Roberta? How is Roberta different than BERT? I don't think they're very different. They are basically very similar with a few modifications. So one of what they wanted to do is basically play with the parameters a little bit more, give it more data, etc. If you look at their conclusions, they say, so let's just say here, they present a replication study of BERT pre-training that carefully measures the impact of many key hyperparameters and training data size. They find that BERT was significantly undertrained and can match or exceed the performance of every model published after it. Our best model achieves state-of-the-art results in all the different, like squad, glue, etc., all the benchmarks. And the results highlight the importance of previously overlooked design choices and raise questions about the source of recently reported improvements. Okay, so that's Roberta, sorry. So their replication study, they have a few modifications that here they are. So our modifications are simple. They include training the model longer with bigger batches over more data. So you can see it's just they gave it more, basically. Removing the next sentence prediction objective. So they took that out they argue that it's not as important, but I don't know about that one. Training on longer sequences. So, longer sequences of text, right? That seems to be pretty good and important. So sentences are too short for transformers, it seems. You want to give it longer text, a little bit longer, but remember you have a limit of 512. This one, dynamically changing the masking pattern applied to the training data. So this is different. So they kind of do it in real time instead of doing it in the pre-processing phase. So they're kind of like doing it on the fly. This was a little bit more dynamic, as they say. They also collect a large new data set, CC News, of comparable size to other privately used data sets to better control the training set. But as you can see, the changes are not that significant, right? So they're not that big. They're just more data, etc. And then they run it on the same tasks, obviously, just to compare to the original work. Here they just talk about the background, so we've talked about that already. No need to repeat that. So this is just all the yeah, so here you look at all the, this is all the background that we've talked about. The parameters, you can read through that. BERT is trained, so this is an important one. BERT is trained on a combination of Wikipedia and book corpus, which totals 16 gigabytes of uncompressed text. So BERT originally was trained just on 16 gigs of data. Okay. Okay. Whereas Roberta, Facebook, their data set totaled 160 gigabytes of uncompressed text. So the difference is from 16 to 106, right? 160 is what they trained on. So it's much, much bigger. You can see that that comes from this CC News. It's like 76 gig. And this open web text is 38 gig. And this stories one is 31 GB. Then they evaluate on the models here, right? All the different models, and then they just show the comparisons, the statistics. And you can see they're showing results here. Somewhere in here they have, yeah, so this is Roberta now. Also, the byte encoding, the subword encoding that they use, I think is consistent with BERT. There's this robustly optimized BERT approach, Roberta. Here's the number of parameters, etc. So they kind of start at BERT large and then go from there. So you can see the model. This is their Roberta versus BERT large. So 13 gigs versus 160 gigs. Batch size is much bigger. And then these are the performance metrics. You can see they're higher and better. Not by much, but just like four percentage points, it seems, on the best ones. Okay, and then, yeah, this just goes into the results of each individual task. You can read through that. Roberta does an F1 score. It's a little bit better than BERT large. XLNet, which is much bigger also, still, they're like 0.1% higher. You can read through the conclusions there. Yeah, so. So you can see here, they carefully evaluate a number of design decisions for pre-training BERT models. They find that performance can be substantially improved by training the model longer with bigger batches of over more data, removing the next sentence prediction objective. So I think they changed this to something else. They didn't seem to like predicting, given this sentence, what's the next sentence? And I believe they changed it to, are these two sentences like related somehow? So kind of what we did today. Training on longer sequences. So more, instead of a sentence, maybe 2-3 sentences, and dynamically changing the masking pattern applied to the training data. And they believe they achieved state-of-the-art results on all these benchmarks. And then that's the data set. And then they have a nice little list of some of the parameters. Here you can see the Roberta base, Roberta large. Large does even better, but it's a monster of a thing. 160 gigs. You can see all the parameters there. Number of layers, number of the size of the hidden layer, attention heads, and so on. So you can see that, and the parameters that they use for different tasks, and that's it. All right, so that's Roberta. So as you can see, Roberta is not that big of a departure from BERT. It's more of a, more data, little things like that. So I didn't see anything that makes it significantly different. And then the last one, are there any questions about Roberta? Guys?
Nope.
All right, and then the last one for today, so we'll cover this one fairly fast. This is Roberta XLM. The paper is called Unsupervised Cross-Lingual Representation, Learning at Scale. This is also Facebook. Now notice this paper shows the pre-training for multilingual language models at scale. And they believe this leads to significant performance gains for a wide range of cross-lingual transfer tasks. We train a transformer-based mass language model, a BERT, Roberta in particular, on 100 languages using more than 2 terabytes of filtered common crawl data. So think about it. BERT was 16 gigs. Roberta was 160 gigs. This one, Roberta XLM, is 2.5 terabytes of data. It's text from 100 different languages. So you had text from French, German, and we'll see in a sec. So there's a lot of data there. And then this text is similar to all the other ones, but you can apply it now for named entity recognition in other languages or other tasks in other languages, I should say. But really, this paper is not that much different. I really just wanted to point out that it's bigger, basically. And I wanted to show you that it was trained on different languages. So it's still, basically it's the same idea, right? So it takes text, but now the text is from 100 different languages. And once you pre-trained it, then you fine-tune it on this normal tasks, named entity recognition, cross-lingual question answering, the glue benchmark, and so on, right? So all of these. And then here they provide the scores, which are good. And then here, you can go through all these details, so there isn't that much to say. I just want to show you one thing. These are the 100 languages that it was trained on. So if you look here, English had 300.8 gigabytes of data. It's the dominant one, obviously, versus like Afrikaans, which is 1.3 gigs. And then another language that's dominant here is Russian. So if you look, Russian is 278 gigs, but something like Chinese traditional is only 16 gigs. So obviously the data is going to be influenced by that, according to this, right? We've said that the more data and the more capacity, the better the model. So you could actually take that to mean that English and Russian will be better than Chinese traditional. It's biased towards them in a sense. All right, and that's basically it for today. You can see also, oh, actually, this is nice. Look at the model architectures and sizes. We've got all of them here, right? We've got BERT base, BERT large, Roberta base, probably Roberta large. And then XLMR is Roberta, XLM. So you can see the tokenizations that they use, word piece, BPE, or sentence piece. And then the number of layers, the number of hidden, size of the hidden layers, number of attention heads, the vocabulary size, the number of parameters. So notice that XLM Roberta has 550 million parameters, but the largest is GPT. Well, actually GPT-2 is big. There's this thing called T5, which has 11 billion parameters. And GPT-3, I'm not sure what that one has, but it doesn't appear in this paper. But this is pretty interesting. It shows you how large these things are getting. Anyway, that's it. Just wanted to go through these 3 papers. So let me go ahead and stop here. I'm going to stop the recording.